All right, well, I've got some homework back for you. And last time we got partway through this problem. Remember, what we're doing is we're proving the correctness of this program. So the program is we have a x, y, and z are declared to be integers. The precondition is x is greater than z, and the postcondition is x is less than or equal to y, or y is less than or equal to z. And the program is this if statement, right? And I think we have this checklist here. Let's take a look. We have this checklist here. Let's review this. P.24, the proof method for this guarded if guard statement, IFG statement, is to prove it, you have to prove these, well, on our P.24 checklist, there's 4 things, but that's because there's 3 guarded commands, right? So the first one, part A, is Q implies B1 or B2 or B3, where those B's are the guards. Here, let's go back one slide.
So it's going to change how many things you have to prove.
Yeah, it's going to change how many things you have to prove, because here is 2, so here there's only 2 guards, here's there's 3, so we don't have as many steps to follow as in this example. All right, and so the first one, part A, is we have to prove that the precondition implies the disjunction of every guard, right? So here's the precondition, x is greater than z, so x is greater than z has to imply, and these are the guards, so x is greater than y, that's this guard, y is greater than z, that's this guard. So, and at the end of class last time, we had just finished proving this. You remember how we did that? It was kind of tricky.
It was like a transitivity.
Yeah, it turned in to be based on a transitivity. How did we get? But how did we get that? Do you remember the trick the technique we used?
Yeah,
we started with the whole thing. We did the contrapositive, and then from that it became apparent that it was basically a transitivity property. All right? Does everybody remember that? And then we stopped right there. So now what we're going to do, we're going to finish this up by doing B and C. Okay? So is everybody with me here? All right. So now, and what are B and C? B and C are, we have to prove these Hoare triples. Well, how do we always prove a Hoare triple? Yeah, we show that the precondition implies the what? The weakest precondition, right? The actual precondition implies the weakest precondition. So here's proof of B. So, and because there's an implies, then usually the technique that we use is what? Assuming the what? Conjuncts the antecedent. So we'll just say, assume, what was that P? What was the definition of the Hoare triple? Did you have a number for me there?
I think it's P4.
P4, right. Okay, so it's assume conjuncts. Assume conjuncts of antecedent using P.4. So let's just go ahead. We don't have to bother writing it out. Let's just go ahead and start with the consequent. So what would the consequent? Yeah, it would be over here. It would be weakest precondition of what? Of this dot this, right? So we start with WP dot, and then what were the statements?
XY gets YX.
XY gets YX dot
X is greater than or less than equal to Y.
X less than or equal to Y,
Or Y less
or Y less than
equal to Z.
or equal to Z. Good. Okay.
P18.
Why the heck not? We got this one down now. P.18, and as long as we're combining steps, we'll do n textual substitution.
Y is less than equal to
So yeah, so let me see. Everywhere there's an x, you replace it with y. Every place there's a y, you replace it with x. So what do we have?
Y is less equal to x, or x is less equal to z.
Right.
Yes, or x is less than or equal to z.
Probably.
Now, what?
No, we don't have one. Well, it's,
Yeah, what now?
We do?
Well, now what? Yeah, what's
if we split the y is less than or equal to x, we have that one.
Yeah, let's look over here what we have to work with. Here's one conjunct, here's another conjunct.
We're close to that one.
We're close to this one, right? But the problem is we have a less than or equal to.
We have that or x is equal to y.
Yeah, we need to pull this out of this one?
Yes.
Is this the one?
Yeah.
It's the only one we can work with because the other one's false, isn't it?
If we assume the
Can we
conjunct?
assume the conjuncts and say or false?
Well, we have to.
Yeah.
Yeah, we have to. Actually, let's do that one first.
Let's do it in one step because we're assuming both conjuncts.
No. Let's assume. If we assume, which conjunct are we assuming?
X is greater than z.
X is greater than z. And then false is the what?
Identity of or.
It's identity.
Identity and an identity of or.
330.
False is identity of or, which is, you say 330, is that what you said?
Can we use a lowercase cursive u as identity?
More abbreviations. Whatever. Okay, so this is going to be or false, and then false. So this is going to be just what? Y is less than or equal to x, right?
Yep.
So this equals, by some math, by the math. Now, so how do we write this?
Y equals x or
Yeah, y is less than x or y equals x. And now we can do what?
assume y is less than x.
Assume conjunct y is less than x,
True or.
True or
which is true or y equals x,
which is a 0.
equals by 0 of or. Zero of or would be true. And since we're assuming the conjuncts of the antecedent, we have to get this to true. Okay? Are we good? So,
Same thing with C.
same thing with C. Should we do it over here? You like over there? Does the camera pick this up pretty good over here? All right. Proof of C. I have a feeling it's going to be similar. So let's just go ahead and start out.
The conjuncts of X.
WP, assume the conjuncts of the antecedent. So what do we do? WP, what do we calculate? WP dot
YZ gets ZY.
YZ gets ZY.
Post condition X is less than or equal to Y.
X is less than or equal to Y.
Or Y is less than or equal to Z.
Y is less than or equal to Z. So equals by our old friend, P.18, and textual substitution will be,
X is less than or equal to z, or z is less than or equal to y.
YZ, X, no, X, oh, X is, oh, I see. Okay, so X is less than or equal to Z. What'd you say? Or?
Z is less than or equal to y.
Okay, so this equals, probably one of these things is going to go away The first one's false. So assume conjunct
X is greater than Z.
x is greater than z, comma 330. So this will be z is less than or equal to y, right? Equals by math. Z is less than y, or z equals y,
Z is less than Y.
equals, yeah, equals by assume conjunct
Y greater than or Z less than Y.
z less than y.
And 329.
Oh, you have a number there for the 0 of or? 3.29 you say?
Yes, sir.
Good deal. True. Boom. Yeah? So these are all pretty straightforward calculations. Now, I think now that we're at the end of the topics that we are going to be tested over on our first exam on Monday. So, but before we start the review, I mentioned in passing last time that I thought that when we were talking about this guarded command language and how if two of the guards are true, one of them is picked at random, and I thought I had remembered it, but I was incorrect. I thought I mentioned in passing that Mathematica has this feature in its language, but it does. I looked it up afterwards, and it doesn't, so I was wrong about that. But I thought it'd be interesting to show you yeah. Here, let me show you. Here's an interesting language. It's called Promula. Okay, I'm not sure about the pronunciation of it, but Promula stands for Process Meta Language, and it is a programming language that is used to for modeling concurrent processes. Now, you learn about concurrency in the programming paradigms course, and so you'll some of the problems that Promula is designed to solve, we'll investigate those problems in the concurrency when we study concurrency in the programming paradigms course. But anyway, here is a little code snip. Here's a little code fragment of a program in this Promula language, and check out what it says, and it works. This is the guarded. It's basically this guarded command that if both of them are true at the same time, it picks one at random. You don't know which one it's going to pick. And look at the syntax of it. It's really kind of slick. So A equals 5, B equals 5. Those are declared to be byte quantities, and then we have another byte quantity, two other byte quantities, max and branch. And look, it uses the exact same if and fi, if and phi, right? For the beginning and the end of the guarded command. And check out the way it works. They have the colon is how they do the, although they need one at the beginning of this, so it's not quite so what the colon does is it's at the beginning of each guard.
So it's not like C++ or GC.
It's not a separator.
It's not a separator, yeah. But check it out. The arrow, is hyphen greater than, right? So that that looks like an arrow. And so here we have A greater than or equal to. In fact, this is this example. Look, this is basically this example, right, of how to do the max, right? So here it is in Promula. So we have guard A greater than or equal to B, then max gets A, and they have this other one. Max gets A, branch gets 1. That's another variable. And then A less than or equal to B, max gets B, branch gets 2, and then phi. And so what happens if A does equal B? Well, either this one will happen or this one. You don't know which one.
You get either branch.
You get either one, yeah. So there you have it in an actual functioning, programming language, in a real one. And there's another one that's a little bit harder to decipher. It's called Occam. And Occam, have you heard of Occam's razor? You never heard of that? It's kind of a philosophical approach. I'm not sure if he was a philosopher. Do you know the story about As simple as possible, right.
That's like the opposite.
Yeah, well, unfortunately, the syntax for this is kind of obscure. I mean, it's kind of hard to see, but remember how we said this is the alternative statement? So alt is the keyword that introduces this is the alternative statement, all right? And the other thing about this is that, you know how we have a semicolon to separate sequential, sequential statements? Well, in Occam you say SEQ, and then whatever is indented from that, the indentation has meaning in Occam. This is like Python. A lot of modern scripting languages this is a trend, are using the indentation to actually have meaning. So you, as opposed to having separators and brackets and stuff, if you indent, then that means it's within the body. And so it's kind of it's starting to catch on now.
Because it looks nice, it's organized.
It forces you to indent correctly.
C++ anyway.
We do it, but you're not forced to. You don't have to. But here you have to. So what happens is, and notice there's no, you don't need anything. It's just the end of the line. It's just the end of the line and terminates the
It
statement.
is nice.
Well, that means if you have a really, really, really long statement, it can be pretty ugly. Because you can't
Yeah.
break down a line.
Well, yeah. There must be a way to account for that. But anyway, so these two statements are sequential. Now, what the meaning of this example is, C1 and C2 and merged are called channels. And so what's happening is this is a communication. This is a piece of code that deals with communication from two channels, C1 and C2. It's getting input from two channels, C1 and C2, and it's sending output through the channel called merged. And you can kind of see what it's doing here. What it does is, okay, so you understand, count 1 is less than 100. Well, that is a Boolean expression, right? Now, instead of ampersand, ampersand, and is just a single ampersand in Occam, right? Which is kind of nice, I think. And then the other one is a Boolean expression also, C1 question mark data. That's a Boolean expression. And what that means is that channel C1 has received data, has received information, data, has gone through channel, channel C1 has received data. So that's either true or false. Right? So that's a Boolean expression, right? And then what happens is, and so that's the guard. All right, so you say alt, and then what's indented is the guard, and then what's indented from that is the body of the guard, is the guarded command. And so what's in this, the guarded command. So the command is count 1 gets count 1 plus 1. So and notice that it uses colon equals for the assignment statement, which is kind of nice. And so count 1 gets count 1 plus 1, and then you send that data through the merged channel. So this is an output expression. This takes whatever data was in it, sends it through the merged channel. And then count 2 less than 100 and C2, so if count 2 is less than 100 and channel 2 has received data, okay, then count 2 gets count 2 plus 1. And then the third guard, so there's 3 guards here, and then status request, so that's a Boolean, and then sequential out, count 1, out, count 2. So, but anyway, so here's, yet another example of an actual guarded command with, and you don't know which one's gonna, and you don't know which of these guards. See, what might happen is,
Rows less than 100.
yeah, so if what this does is that if one channel happens 100 times, if it gets up to 100 before the other one does, then that guard will always be false. And the other one, but if they're both less, if the counts for those inputs are both less than 100, they'll be getting it, and as they receive data, and if they both receive data, well, one at random will get its thing. See, so it's kind of easy to understand. But the whole concept is the same concept of this. It is this guarded command if statement, this if guarded command statement. I don't know, and I don't know that much about Occam to know if you can do count 1. Probably not. I mean, by looking at how they had everything written out explicitly, I doubt it. But so anyway, those are some actual. I thought that would be interesting. Those are some actual examples of the guarded command language, and I think another interesting thing about this is that both of these languages that use this statement are dealing with concurrent processing, stuff that happens at the same time, right? And so, and this non-determinism in the if statement is appropriate for that kind of situation. It's not a coincidence that these are concurrent, that these are languages that deal with concurrency. See, you guys know what we mean by concurrency. See, whenever you program in C or C++ or Java, it's possible to have, in Java to implement separate threads, but probably most of the programs that you've written so far, your program, it does one thing at a time, and it does, and if you have an if statement, it might go do this and this, and if you have a loop, it might go branch and do this and this again. But what's happening is there's only one processor that is executing your program at a time, and it goes linearly through the program. It might repeat some stuff until it gets to the end. But with concurrent processing, what happens is you can fork off and have two different parts of your program executing literally at the same time. That's what concurrent processing is. And the reason it's becoming more and more important is because the CPUs, like in your laptops now, I don't think it's even possible to buy a laptop that doesn't have more than one core. Have you heard of multi-core CPUs?
Oh, yeah, I think dual core is.
Dual core is kind of like the standard now. Well, that dual core, those are two different parts of the program are executing literally at the same time because they're running together. So the way you program to have that concurrency happen is it's becoming more and more important as time goes on.
And can you tell like C++ to do that, or do you need
You can do that from C++, but you need to use a library. So it's not built into the language. You call there are thread libraries, and so you call these threads. You fork off a thread. And that depends on the library. Same with Java. With Java, you fork off a thread using the standard Java libraries. So that's not part of the language. There are some languages that have concurrency built into the language itself. The most notable example is Ada, a programming language called Ada, A-D-A. It has concurrency built into the language itself, as does Occam.
apparently?
Yeah. All right. So that's the end of the material. Now we have an exam coming up on Monday, and I thought we'd just spend the rest of the day starting our review. The Towers of Hanoi, Hawaii. Do you have a?
Still working on recursion.
Oh, you're working on recursion in your programming class. So maybe what we should do is talk about your problems in your programming class. All right. In your whole career. Yeah, that's right. We're doing it in assembly language now.
Oh, really?
Yeah. You'll revisit that. That's a classic problem. Every computer science student knows what the Towers of Hanoi problem is. Okay.
My brother mentions it.
Oh, does he still remember? Yeah.
14 years later.
14 years later.
He's like, "You done Towers of Hanoi problem?"
Yeah, 14 years later, he still remembers Towers of Hanoi. And then when you do concurrent processing, can you tell me what is the classic problem in concurrent processing? It's not the Towers of Hanoi, it's the what? Yeah, the dining philosophers. There's another problem that's, dining philosophers is to concurrent programming as Towers of Hanoi is to recursion. So anyway,
You guys heard of the Queen's problem?
yeah, that's a good one, but we don't do that one. The Queen's problem. It's to place all 8 queens on a chessboard in such a way that they're not attacking each. No, wait, no, that's not right. What is the 8 queens problem? It has something to do with placing 8 queens on a chessboard.
I think it's that so that none of them can.
No, I don't. But that's impossible.
No, it's not.
Oh, maybe that's the problem.
That's why.
Maybe that's why it's a tricky problem. Yeah, it might be to place 8 queens on the chessboard so that no queen is attacking any other queen.
I want to do that right now.
Because they move horizontally, vertically, in either diagonal. So you have to put them like a knight's move away.
Right, a knight's move.
Anyway. Yeah, I haven't really investigated it. Yeah, and one on each column. One on each row and one on each column, but not, yeah, I think that is the problem. I think that is the problem. All right. Well, we started with mathematical induction. So how about everybody get out a piece of paper? And we'll just have this be a little workshop.
All right.
All right? And I'll give you some problems for you to work through. So you guys out here in video land, that's you too. You also. So get out a piece of paper, pencil, and do this. So let's prove by mathematical induction that, prove by, let's do just a few of these. So let's do, oops, not a very nice looking signal. Sum on I, 0 less than or equal to I less than n, body, 2 times I plus 1 equals n squared for n greater than or equal to 0. Now, I think on this, probably what we'll do is have a lot of cuts. Yeah, I mean, they can just pause. Well, so, but we'll just cut into a transition, you know, the fade in, fade out.
Oh,
Okay, so are we good? Who? Do you need a hint?
no, I got it.
You got it, it's just,
Working.
okay,
So we can start one.
Doing all the work properly, you know?
right.
No short.
And the base case, okay, so the base case is, well, how do you know what the base case is?
N equals 0.
N equals 0. And if you do n equals 0, 0 less than or equal to I less than 0 is empty range. Empty range is, yeah,
0 and 0
is-
equals 0. So that's the
right. And then you must prove
sum
sum
over
of I
0 less than or equal to
I less than
n
n plus 1
equals 2
equals 2 times,
times is equal to
or 2 times I plus 1 equals n plus 1 squared, assuming sum on I 0 less than I less than n equals n squared as the inductive hypothesis. Okay, here's the next one. I'm assuming you guys out there in video land can pause while you're.
How does the split off term work on that?
Oh, the split off term. You're gonna have this on the split off term. It's gonna be, you're gonna have sum on I 0 less than or equal to I less than n plus 1, body 2 times I plus 1. And then you're going to split off the term is going to be what?
2n plus 1. Oh,
Sum on I 0 less than or equal to I less than n. And the last term here is n. Is there something else out here?
No.
Or not yet? Okay, so this is going to be n.
Body,
So body
2i plus 1.
2 times I plus 1. Now the last term here is the n is n, right?
Plus
So this is 2 times n plus 1. So this is plus 2 times n plus 1. Right?
Just factor.
Yeah. Okay. So this is how you split off the term from in this problem, in the proof.
And then you use some inductive hypothesis. trait.
And then the sum, yeah, inductive hypothesis, and then you do some math, and then, okay? Now, how about this one? Prove by mathematical induction 2n plus 1 is less than 2 to the n for n greater than or equal to 3. Now these are tricky these are a little tricky, these inequality ones. Okay, so you guys can pause.
Question.
Mm-hmm.
When it's n, for example, n greater than 3,
That's your base case.
is the base case 2?
Oh.
No, if it's n greater than 3, the base case is 4. If it's n greater than or equal to 3, the base case is 3.
So it's whatever the closest integer actually
It's the,
equals.
yeah.
Okay.
Yeah, yeah. Now this is a little tricky, right, when you get to the inductive step. Shall we work through this one? The inductive case,
Prove 2 times n
prove
plus 1
2 times n plus 1
plus 1 is less than
plus 1 is less than 2 to the n plus 1. Must prove 2n plus 1 plus 1 is less than 2 to the n plus 1, right? Assuming what? 2n plus 1 is less than 2 to the n as inductive hypothesis, right?
Right.
So I think what you want to do is start with this side.
So you do start with one side only?
Yeah, I think, as I recall, you start with this one, right? Because 2 to the n plus 1, so I think it's like this. 2 to the n plus 1 is equals, by math, 2 times 2 to the n. Is that right?
Yeah.
And now we can use the equals by the inductive hypothesis. This is greater than. Is this right?
Yeah, it's greater than something.
This is greater than, by the inductive hypothesis, what? Well, we know by the inductive hypothesis that 2 is greater than this, so 2 times this must be greater than 2 times this, right?
Okay.
So this is greater than 2 times 2n plus 1, right? Am I going in, has somebody done this? Am I going in the right direction? Is it going to work?
I haven't finished it. It started before.
Okay, well, I don't have any notes here, so you guys are going to have to help me out.
Well, so then math.
So by math, now what are we trying to get this to be greater than? We're trying to get this to be this,
2n
right?
plus 1 plus 1, which is 2n plus 3.
So this equals by math,
4n plus 2.
this equals by math. Now we're going to have to do some tricky math here, I think. What we want this to compare this to is 2 times n plus 1 plus 1. I mean, here's what we want it to be, right? Here's what we're trying. Here we're trying to compare this with this. So let's go ahead and write this down. 2 times n plus 1 plus 1. Now, plus what? For these to be equal. For this to equal this, does everybody see what we have to do here? We have to do some fancy manipulation. Well, how many n's do we have up here?
4.
We have 4. How many n's do we have here so far? 2. So we need 2 more n's, right? So this is plus 2n. And now how many units do we have here?
4.
No, I think we have 2.
2, sorry.
And how many do we have here so far? 3.
Minus 1.
So we have, this has to be minus 1, right? Is that good so far?
Yeah.
Math.
And now what we are claiming is that this, we need to have this be greater than this, right?
Right.
So let's just state that. Is greater than what? Oh, and for what reason here?
Because we're adding 2n minus 1.
Here, so it's greater than,
Because math says so.
greater than 2, what is it?
Times n plus 1.
n plus 1 plus 1. 2n plus 1 plus 1. Because what did we, because why?
Because it's adding a 2.
Because we know that 2n minus 1 is, we're dropping this positive quantity.
And it's greater than 5.
2n
And the reason is because why? Is because 2 and minus 1 is positive. Yeah, because 2n minus 1, it's positive, right?
Or
Is-
positive for n is greater than
Yeah, maybe if we,
3.
should we write out it's positive? No, we can. Because this is greater than 0 for
N greater than.
our thing is n greater than in our range, right? That we for n greater than or equal to 3, right? Does everybody see how we can make this statement? So yeah, that's kind of tricky. Yeah. All right, so now, well, since that one's kind of tricky, maybe we better do another one. Okay, let's prove this. Prove n squared is less than or equal to 2 to the n. N squared is less than or equal to 2 to the n for n greater than or equal to 4. Now, guess what? Do you remember this one?
Do I remember it?
Yeah, you remember doing this one?
I think so.
Guess what we are going to use in this one?
Man.
Well, but we are going to use math. What
Okay,
else?
good.
We're going to use look. We're going to use this that we just proved. Do you remember doing that?
Yeah, because n squared times 2n plus 1 is n plus 1 squared. Got it.
Okay. Okay.
And we're allowed to do that?
Well, sure. I mean, that's a previously proved. We just proved it, right? So that's previously proved.
If we've had this one on the test,
Well, that's a good question. I would either have to have you do both of them, or I would have to, on this one, I would have to say you may use the fact that and quote that one. Yeah. So let's do it.
base case,
Base case.
16 is
The base case is n equals what? 4, right?
16 is less than or equal to 32.
No, I think it's
2 to the 4th. 16 is less than or equal to 16.
less than or equal to, yeah. So base case is 16 less than or equal to 16, right? And then the induction case is what? Must prove n plus 1 squared is less than or equal to what? 2 to the n plus 1, assuming what? N squared less than or equal to 2 to the n
Start at the right side.
as inductive hypothesis. I think you start at the right side again.
Yeah.
Okay, so I'll let you do that. So again, I think you would start with the right-hand side, right?
Yeah.
And do 2 to the n plus 1 is 2 times 2 to the n, right?
Inductive hypothesis.
And then inductive hypothesis, that's greater than or equal to what?
N squared.
N squared.
Yeah, but it's 2 times, right?
2 times n squared.
How is that going to work? How are we going to do this?
Well, then don't we kind of
2 to
that
the
equals
n plus 1.
n plus 1 squared and modify it?
Oh, right. It's the same technique.
Right.
Because we want to get that n plus 1 squared and then figure out what's left over.
Right.
And then what you have left over is there's going to be a 2, there's going to be a,
2n plus 1.
yeah, there's going to be a 2n plus 1 and what's left over, I think. Right?
Yeah, we have n plus 1 squared plus n squared minus 2n plus 1.
Plus 1, yeah. And so then you can use the previous one.
To say 2n plus 1 is less than.
Yeah. Yeah. Oh, that's good. All right. Good job. And we will continue our review next time.
Okay.
Okay?